Hi, in the last session, we designed a project using finite state machines and we learned what are finite state machines, how they work, and how to code them in VHDL. Now let's talk about some good design practices in FPGA and VHDL designs. These tips and tricks are really important to learn and understand to code more robust and efficient designs. So let's start. Well, the most important thing is the code readability means your VHDL code should be very clear to understand. And for that, always use meaningful names for your signals, your process, your generics, your data types, constant and entities, etc. Or any of the identifier you are using in your VHDL programming. And there are many benefits of it. Like your code can be easily understandable. It will have lesser bugs or debug will be easy and it will also ease any future improvements. Next thing is indentation. This is again important for code readability. We will understand it in the next slide in more details. But a quick brief that indentations are applied either by the tabs or spaces. Although spaces is much better choice when you are working on the different editors for your coding like Quarters, Notepad++, Notepad, etc. Because sometimes different editors display tabs with the different gaps and it can create some difficulty in your code mapping. But here the only point is to use indentation in your code, either tab or spaces. So let's understand this in the next slide. These are two VHDL codes here. If you closely look into it, you will see that both codes are same and they will do the same thing as well. But the only difference is that they look different because in the left, we aligned every statement based off its group, like what is inside if condition, what if inside process block, what is inside their case statement, etc. So you can clearly read this and understand this, right? But look at the right side code. Here also every statement is same. But can you read it easily? No, right? Because now you need to highly concentrate on each statement that in which group or hierarchy it is placed, right? So tell me that in which section of code you are more comfortable to read and understand. Left one or right one? Left one, right? Because here we have used indentation, means we just align them by adding some additional tabs or spaces before the statement. And that's it. So you have choices. Either use tab keys or few spaces. But I recommend spaces, especially when you are working on the different editors for your code. Reason is simple that sometimes tabs get misaligned on different editors, but spaces are equally treated in all the editors. But when you use spaces, you enter at least 4 or 5 spaces to align your statements, unlike tabs, which is just a single press. In most of the editors, these are automatic and they are smart enough to add them. And some editors also give you choices as well. This is quite simple, I think, but important. Next tip is always try to avoid generation of latches in your designs. We have already covered this previously, but a quick brief here. Well, you do not design latches in your VHDL code specifically, but they get created in FPGA, especially when you are not careful in your branching of all the possible options in the conditional statements. Latches are generally not recommended in FPGA designs. They can be created with the combinational process block, but not for the registered process block. We already explained this, that why this happens. So any incomplete conditional statements like incomplete if statement or switch case statement in a combinational process will have high chances to generate these latches in your FPGA. So ensure that each and every possible condition is covered in the combinational process blocks. Now Clock is one of the important part in FPGA designs, and they are widely used in digital systems as well. And in maximum designs, they are external elements like coming from oscillators or clock drivers or clock generators, etc. Means some other component or external component. But the problem is that these components generally comes with a fixed oscillations and your needs might be different from a different projects. In such cases, we adjust that clock cycles based on our project needs. And this can be done through your VHDL codes. For example, you have a 50 megahertz clock connected to a FPGA pin and you need a 25 megahertz clock or you need a 1 hertz clock cycle for a digital watch. So for this example, we can generate a 25 megahertz clock using a register and a NOT gate like in this block diagram. So you input 50 megahertz as an input clock and 25 megahertz at the output of this flip-flop. And output of this flip-flop will be your clock signal for the rest of your designs, like you seen in the next slide. So you can see that FF1 has a 50 megahertz clock. Then its output goes to FF2 and this signal will have 25 megahertz of clock for FF2. However, this will work fine, but this type of designs is not recommended because there are some practical issues in this design. One issue is routing delay for 25 megahertz clock. That may come from your clock to output delay of FF1. Now understand what are the problems when you generate your clocks using the logical elements like we did. So your FPGA can have multiple regions from where it can get external clock signal. So your routing or placement of elements can create problem. Delay of your clock signal can also vary depending where that flip-flop is located inside the FPGA. Remember that synthesizer can place this flip-flop in any location inside the FPGA. So delay can be different for each combination. Means delay can be different from one FPGA to the another FPGA. Also, these delays also affected by the given voltage and temperature. Means it can have environmental impact as well. So this is not a practical or a real life solution. Remember that you will not see those issues in your behavior simulation because these are practical issues. Also, vendor tools such as Quartus Static Timing Analyzer, they also struggle in analyzing clocks if you generate them like this. So try to avoid using them like this. So what is the good approach then? The better solution is that use PLL or phase log loop to generate this 25 megahertz clock. Modern FPGAs typically have these built-in PLL resources and they are very easy to use to generate various clock frequencies. PLL or phase log loops can directly drive your global clocks in your FPGA designs. Also, if you are doing this, then this is also not a good practice. Like when you add some gate or elements on your clock signals. So here goal is to capture input A only when this enable signal is applied. And this method is not recommended because these additional logical gates before the clock signal will add logical delays in your clock path. Also, as I said that applied voltage or temperature can also affect these delays. Means they can malfunction based on the external things or environmental changes. And it can also limit your maximum operating frequency of for your designs. So avoid this kind of approach in your designs. So the question is how to do this. So let's see in the next slide. So this is a better way of doing that. You can see that we didn't touch our clock signal. Instead, we applied our logic on the D input or input port. So we added a multiplexer on the data path, not on a clock path. This multiplexer will ensure that you will get input A only when this enable signal is applied. So your clock signals remains unaffected by any logical gate delays, and it is directly reaching to your flip-flops without any additional component between them. So this system has better timing margins compared to the last one, and it can operate at the higher clock speed as well, means better operating frequency. Even some FPGA architectures provide some flip-flops with dedicated enable pins, like in this block diagram. In such cases, your synthesis tool will integrate that without any additional component. So this is a simple VHDL code for what we are discussing. And this code can implement any of the circuits below, depending on what type of architecture you have. If your FPGA have this element with enable pin, then it will use that. Else it will add this multiplexer design. So you can see that how easy it is to code them in VHDL. Just remember, avoid using the gate structures on the clock signal until there is no option you see to fulfill your project needs. Although this is very rare or unlikely. Okay, so that's it for today. We discussed some of the good practices for your VSDL and FPGA designs. We learned how to improve code readability, how to use indentation in your VHDL code, how to avoid latches in combinational circuits, and what are good structures when you are working with the clock signals. In the next session, we will continue with more tips and tricks to make your VHDL designs more agile and flexible and more reliable at the same time. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.